So, good evening. As no one has joined till now, I will wait for 10 minutes and then I will start the session at 6:10 p.m. Good evening, everyone. Uh, so let's start with week 9 session of Biomass Conversion and Biorefinery. The course coordinator for this course is Professor Kaustav Mohanty from the Department of Chemical Engineering, IIT Guwahati, and today Arihant Ahuja. I'm your PMRF TA who is working under the guidance of Professor Vibhor Kumar Rastogi, Department of Paper Technology, IIT Roorkee. So we will start the session by discussing about the questions which you have submitted this week, that is week 9 assignment of 2023, and we will discuss the answer and the logic behind those answers so that you can grab your uh, uh, details carefully. And after that we will discuss about the week 10 preparatory questions, and this week 10 preparatory questions will help you to prepare for the next week question answers. So now let's start with week assignment 9 of 2023. The first question for assignment 9 of 2023 was the smallest unit in the cellulose structure is considered as elementary fibril, a bundle of 30 to 36 cellulose chains bounded by. So we all know that what is cellulose. By far we have seen cellulose a lot of time, and it is a part of biomass, and we get this from the lignocellulosic biomass structure. We separate the lignocellulosic into lignin, hemicellulose, and cellulose. And these cellulose are carbohydrate polymers. So these are of carbohydrate polymer. And this cellulose has fibers in it which are bonded with some bonding, and that bonding is known as hydrogen bonding. So therefore the answer for this question is hydrogen bonding. So this is a typical cellulosic fiber illustration of cellulosic fiber. So inside a cellulose fiber there are microfibers, and that macrofibers, and that macrofibers is micro, and these microfibers is elementary fibers. These are single elementary fibers, and the bonding between them is due to hydrogen bonding, which helps to give cellulose its good tensile strength. So, elementary fibrils are the smallest unit of the cellulose structure. They are composed of bundles of 30 to 36 cellulose chains that are held together by hydrogen forming a long and stable chain. Elementary fibrils are further assembled into large structures such as microfibrils, which can be assembled into cellulosic fiber. Hydrogen bonding is an important intermolecular forces that contribute to the stability of cellulose fibrils. In cellulose, each glucose unit is linked to its neighboring unit via hydrogen bonding. So we have seen that all the um, fibers, all the elementary fibrils are linked together via hydrogen bonding. These hydrogen bonds form a strong and rigid structure that gives cellulose its high tensile strength and resistance to degradation. So now let's move on to the second question. Which is the correct sequence for steps for ethanol production? So to produce ethanol from biomass, some type of steps are done, and these steps are done like first we do the milling, then cooking, then liquefaction, and finally fermentation. So milling is a process in which we uh, break the larger compounds into smaller compounds, and then we cook it so that we can separate the materials present in the biomass. After the cooking, we do the liquefaction. That is, uh, we make the polymers convert into monomers, and these monomers are soluble in well form. So therefore, this is known as liquefaction. And finally, these soluble forms of monomers are fermented to produce ethanol. Therefore, the answer is milling, cooking, liquefaction, and then finally fermentation. So this is a typical block diagram of the process. So we can use any biomass, and after storing it we do the milling, in which the larger particles are broken down into smaller particles. After that we cook it, and this can be done in alkali, acid, or organosolvent, or enzymatic treatment. There are many different techniques, and we have seen all these techniques in past weeks also. After the cooking we do the liquefaction, that is we convert the polymer chains to monomer chains, such as to we convert carbohydrates to soluble sugars. So these soluble sugars are done during the liquefaction process, and these soluble sugars are then fermented so that we can get ethanol. This ethanol has many impurities in it. So yes, we have got ethanol, but we need to purify it. So for purification we do the distillation, and finally we get the purified ethanol. During this distillation we also get some type of solid reject material, and these are sent for distilleries grain, and which can also be valorized in other ways. So to produce ethanol from biomass involves four steps. First is milling, the process of breaking down the biomass into smaller particles. And why do we do this? We do this to increase the surface area for enzymatic hydrolysis or fermentation or any other processes. Second is cooking. This involves heating the biomass in the presence of water and dilute acid or an alkali or organosolvent and many other things. And this helps to break down the complex polysaccharide into simpler sugars. Or this is also done to separate the lignocellulosic biomass. After the separation of lignocellulosic biomass components, we do the liquefaction. The liquefaction process involves the addition of enzymes to the cook and cooled mesh to break down the remaining starch into simple sugars, which are also called soluble sugars. And finally, we do the fermentation. This step involves the conversion of simple sugars such as glucose or fructose, which you have got from the liquefaction step, to convert these into ethanol by the action of yeast or enzyme. And finally, there is a fifth step, that is distillation, which is done for the purification of the bioethanol. I hope that these five steps, now these four plus five, fifth step distillation, you have understand that what is the sequence of these steps. So now let's move on to the next question. Cellulose is a high molecular weight homopolymer consisting of. So we know what is cellulose. It is a polysaccharide and it is a type of carbohydrate, and it contains d-nitroglucopyranose units. So let me show you what are these units. So this is a typical structure of cellulose, and in this part is anhydroglucose unit. These anhydrous glucose unit are joined by the beta 1,4 glycosidic bond, which is known as COC. This this is a particular typical structure of cellulose, that it is made up of anhydroglucose unit, and these are bonded together with the beta 1,4 glycosidic linkages, also known as ether bonds or COC linkages. So D-nitroglucopyranose units are monomeric units which make up the molecular linear chains of cellulose. So these are the monomer units of what? Of cellulose. Uh, in short, we also call DAG. So what it is, DAG is a cyclic form of glucose where the oxygen is in the ring is removed, resulting in a loss of water. And DAGs are linked together by beta 1,4 glycosidic bonds, forming a long linear chain, which are represented by ether bond or simply COC linkages. These chains are stabilized by interchain hydrogen bonding between the hydroxyl groups of glucose, resulting in the formation of microfibrils, which are the basic structural unit of cellulose. Now let's move on to the fourth question. In acetogenesis step of ABE fermentation, the substrate glucose is converted to. So first of all, what is this ABE fermentation? In last week also we have discussed heavily on this, and this is used to make three chemicals such as acetone, butyric acids, and ethanol. So these three are the major components, and that's why we call it ABE fermentation. In the acetogenesis step, which is the first step because it consists of two steps, this one is the first step, acetogenesis. The glucose is converted into acetate and butyrate. So, ABE fermentation is a biphase process, which we have seen in the last week lecture also. It is a biphase process because it takes place in two steps that convert sugars into acids and finally into solvents. So the first step to convert the sugar into acid is known as acetogenesis method. So during this first step, acidogenetic bacteria, a typical bacteria which is known as acidogenic bacteria, is used to produce acetic and butyric acid from sugar. And the second step is known as solventogenic bacteria, which is used to convert acetone, butanol, ethanol. Therefore, when we get these three solvents, acetone, butanol, and ethanol, that's why it's known as ABE fermentation process. So, therefore, ABE fermentation process is a combination of two steps. So we have seen that it is a combination of two steps. First is acid fermentation phase. And acid fermentation phase, we are converting the glucose into acetate and butyrate. So that's why the answer is that in ABE fermentation, in acidogenesis stage, we convert glucose into acetate and butyrate. And further, these two are converted into ethanol, acetone, and butanol, which is known as solventogenesis phase, and which is the second step. So, in the acidogenesis phase of AB fermentation, the substrate glucose, this glucose is converted to a mixture of organic acids such as butyric acid and acetates, acetic acid and butyric acid. The production of acetone, butanol, and this occurs in the solventogenesis step, which is triggered by decrease in pH and accumulation of organic acid, which is the second step. That's why it is known as biphase. Now, let's move on to the next question. What are the major advantages of simultaneous certification and fermentation? So, simultaneous certification and fermentation means that both of these processes are taking place in a single step. These both will occur in same step. So it is known as simultaneous saturation fermentation. In short, we call it SSF. So what are the advantages of it? Is it lower process time, lower enzymatic requirement, or less reactable? So we know that we are doing two steps in the one place. So lower process time is not the answer. Less reactor volume because both are happening inside a reactor only. So yes, lesser reactor volume and lower enzyme requirement. So therefore the answer is both B and C. So simultaneous saccharification and fermentation, or short for SSF, is a process used in biotechnology for the production of biofuels, particularly ethanol. It involves the simultaneous conversion of starch or cellulose into glucose. So we convert the starch or cellulose into glucose and the fermentation of glucose into ethanol by microorganisms such as yeast. So what we are doing here, we are converting the starch or the cellulose, which are the basic polymers present in our biomass, and we are converting this into glucose. And further, we will convert the glucose into ethanol. Starch to glucose and glucose to ethanol. And these two are happening in only single step. Therefore, single. The name is simultaneous acidification and fermentation. The process is carried out in a single vessel, so therefore the requirement of a reactor vessel is also less. It will happen collectively in low volume, and in this the substrate is mixed with the enzyme and microorganisms in the presence of water. So both enzymes and microorganisms will be present, which will convert it into the uh, sugars and then simultaneously into ethanol. The enzymes break down the starch or cellulose into glucose, which is the fermented by the microorganisms to produce ethanol. The process is advantageous as it reduces the overall process time and increases the yield of the desired product. So this is a typical block diagram of the process, and in this, the biomass is first pre-treatment so that we can separate it into lignocellulose, hemicellulose, and cellulose into its individual form. And then we will take the starch or cellulose, and then it will go through enzymatic hydrolysis as well as fermentation. So both enzymes and microorganisms will be present in this reactor. It is a single reactor and it will have both enzymes also and microbes also. The microbes will do the hydrolysis, microbes will do the conversion of cellulose to sugars, and this sugars or glucose, and this sugars and glucose will be converted to ethanol by the fermentation process with the help of microorganisms. So we'll get ethanol. So these two steps we'll come doing in a single reactor, and hence we will use lesser time and lesser volume, and we will also be requiring less amount of organisms. And finally, after getting the ethanol, we will do the distillation so that we can get a purified form of ethanol. And there might be some type of lignin, also residual lignins, which we can do the washing and get the lignin again. And the liquor which was used, the solvents which are using can be recycled back again for this process. So in SSF, the enzymatic hydrolysis of fermentation occurs simultaneously in the same reactor, which eliminates the need for a separate hydrolysis reactor and reduces the enzyme requirement. And additionally, as the fermentation process starts during the hydrolysis step, because we are doing the fermentation during the hydrolysis process only, so the product is continuously removed, which prevents the inhibition of enzymatic hydrolysis reaction and improves the total efficiency of the whole process. So the efficiency of the process is also increased. This also reduces the reactor volume needed to produce the same amount of product, which can lead to significant cost savings. So therefore, SSF process is a highly cost saving, and less amount of volume of reactor is also required. So it is highly cost saving method to produce ethanol from the biomass. What is the function of endoglucanose enzyme in the cellulose system for the bioconversion of cellulose into glucose? So, first of all, what are these endoglucanose enzyme? Before discussing the answer, we'll discuss that what are these endoglucanose enzymes. So, endoglucanose enzymes are those enzymes which hydrolyze the internal bonds of cellulose, and it is a type of enzyme which is used for hydrolyzing the cellulose. So basically, to break down the cellulose, we use endoglucanase enzymes. It is a key enzyme in the cellulose system and plays a major role of bioconversion of cellulose into glucose. So not all enzymes can convert cellulose into glucose. Only a uh, particular enzyme such as endoglucanase can be used. So these endoglucanose break down the internal chains of cellulose, generating shorter oligomers and exposing new chain ends for further hydrolysis of by exoglucanose and beta glucosases. So, in order to break down the cellulose, endogluconase, this enzyme alone cannot break down the cellulose wholly. So this enzyme plus exogluconase and glucosidases are required. So all these three enzymes are required to break down. But this endogluconase is only required to break down the beta 1,4 glycosidic bond. So therefore, the correct answer for this is that endogluconase enzyme are used to only hydrolyze the beta 1,4 linkage in a random manner. Now, what about the other bonds? How do we break the other bonds? So, if we look at this typical diagram of chemical structure of cellulose, so this bonds, beta 1,4 bonds, are broken down by the endoglucanase, and after this breaking, exogluconase is another enzyme which is further used to break down the other bonds present in the cellulose. And finally, beta glucosidase is used to break down the other ether linkages present in the cellulose. So, endogluconase hydrolyze the cellulose to convert it into cellulose, and exogluconase plus beta gluconase are used to break down the cellulose to glucose. So, therefore, three different types of enzymes are required to break down the cellulose ultimately to glucose, so that we can get a soluble sugar and we can ferment this soluble sugar to get bioethanol. So the function of endogluconase enzyme in the cellulose system for the bioconversion of cellulose into glucose is to hydrolyze the beta 1,4 linkage in a very random manner. And this enzyme cleaves the beta 1,4 glycosidic bond within the cellulose chain, creating new chain ends and generating soluble oligomer of varying length. And these oligomers, such as cellulose, this soluble oligomer are further hydrolyzed. These are also further hydrolyzed with the help of ex- exogluconase and beta glucoside to produce glucose. So now let's move on to the next question. Which microorganisms is most widely used for commercial fuel ethanol production from sugars to starchy feedstock? So for now, we have seen that enzymes are used to break down cellulose to glucose or sugars. But how do we break these to get ethanol? So this is done by fermentation process, and microorganisms are required to convert these sugars to ethanol. And the most widely used microorganism in this process is S. cerevisiae. Uh, so, S. cerevisiae is a species of yeast that is commonly used in industrial biotechnology, including the production of ethanol from sugar and starchy feedstock. And this is a typical image of this yeast, S. cerevisiae. It is a type of unicellular eukaryotic microorganism that can effectively ferment glucose to ethanol through a process called alcoholic fermentation. So, what we are doing is we are fermenting the glucose by a yeast which is known as S. cerevisiae, so that this glucose can be converted to ethanol by the process known as alcoholic fermentation. So this is the most commonly used microbial species throughout industries for the production of bioethanol from the sugars. S services has several advantages for industrial application, including its ability to grow rapidly and tolerate high concentration of ethanol, and as well as well-studied genetics and psychology, physiology. These traits make it highly reliable for efficient organisms of commercial fuel ethanol production. We know that there are many organisms which can easily uh, be which can easily die with the presence of alcohol. Ethanol is also known as is also a bacterial suicidal. So ethanol can uh, make the microorganisms uh, growth less or die. It kills the bacteria. Ethanol basically kills the microorganisms. So we need some type of bacteria which is resistant to the high concentration of ethanol, and S. cerevisiae is one of them. This is one of the yeast which is resistant to a high concentration of ethanol. Therefore, this is used for ethanol production in industrial applications. The glucose chains in the cellulose have. So far now we have seen what is cellulose. Cellulose is a carbohydrate. It is a polysaccharide. It has a 1,4 glycosides bonds, which are also known as COC linkages, and it can be broken down into smaller soluble sugars such as glucose. So, but these uh, cellulose bonds have some endings and openings. So there are rings of ethanol and some they're bonded with COC linkages, but at the end there are uh, two more chains which are known as reducing and non-reducing ends. So we know that this is a typical structure of cellulose. It has an hydroglucose unit, and this is known as glycosidic bond. But it is joined by non-reducing and reducing end, and this is known as cellulose unit, which can be easily attacked by the uh, microorganisms. So therefore the answer for this is that the glucose chains in the cellulose have one reducing and one non-reducing end. Now let's move on to the ninth question. The biomass death kinetics in ABE fermentation are described by. So in ABE fermentation, we have seen that we are converting the biomass into acetone, butanol, and ethanol, three solvents, by a two-phase process. Both the two-phase are fermentation process, and so the during this fermentation process, the uh, the microorganisms can also die with the amount as the amount of ethanol or the solvents increase. So therefore, the death kinetics of these is described with the first order expression. So death kinetics refers to the rate at which microorganisms die during the fermentation process. In ABE fermentation, the biomass death kinetics are important because they can have a significant impact on the overall process and process yield. Now, the last question of 2023. What are the disadvantages of using ionic liquid as a pre-treatment method? So we know what are the pre-treatment method. There to convert the cellulose in to convert this cellulose into the soluble sugars. We first need this cellulose or hemicellulose separately from the biomass. So this is done by pre-treatment, and this pre-treatment can be done by alkali, acid, uh, it can organic solvents, supercritical fluids, and also by we can also do this by steam hot water steam. There are various methods, and every method has its own advantages and disadvantages. One method is more in this, and that is ionic liquids, the use of ionic liquids. So ionic liquids are some special liquids of made by salt, and these have the capability to dissolve cellulose in it. Some ionic liquids can dissolve cellulose, and so we can get the cellulose in dissolved form. It has a advantage that we can dissolve cellulose and by the ionic liquid, but the thing is that it has two major disadvantages. First is that it is expensive, and second is that requirement of washing before use. So these two reasons are the reason that ionic liquids are not currently used in industry, because to produce anything in high amount, main things come is cost. So major disadvantage for this is expensive in nature. So, but first of all, what are ionics? Ionic liquids. So ionic liquids are type of salt that exist in a liquid state at around room temperature. They are made up of large organic cation and small inorganic or organic anions. They may have properties such as low volatility, high thermal stability, and high ability to dissolve wide range of substance, including biomass. So they have a lot of advantages. Unlike other alkalis, they are highly stable. They can also dissolve biomass in it. They are low volatiles, unlike the organic solvents. So they have their own advantages, but the thing is that they are very expensive. So liquids are being explored as a potential for the pre-treatment of lignocellulosic biomass for biofuel production because of their ability to selectively dissolve. This is the major advantages of it, that we can completely dissolve cellulose from the lignocellulosic biomass, and then we can get the pure form of cellulose just by dissolving it, and then we can further uh, convert it into sugars and then into biofuel. So this is a potential method for future, but right now the it is being explored so that we can reduce the cost of this process. So this is a typical uh, method to dissolve the to separate the lignocellulosic biomass from the to separate the cellulose from the lignocellulosic biomass. So we know that lignocellulosic biomass has three components: cellulose, lignin, and hemicellulose. And the ionic liquids and water mixture have a selectivity towards cellulose. We can dissolve these cellulose by using some particular ionic solvents, and this can result in the dissolution of which can result in the separation of lignins from the cellulosic pulp and ionic liquids. So this is an easy way to remove the lignins from the cellulose, but is generally expensive. So it holds the potential to in the future, but right now it's in research area. So so far, we have discussed the assignment 9 of this week, and you all have solved these questions of assignment 9, and now you know the right answer of it and the reasoning behind it. Now we will discuss about the week 10 assignment. So week 10 assignment is due next week, and to solve it, so that you can solve it easily, I have prepared some questions for you, and which will help in brainstorming you for those assignment 10 question. So let's begin. In the photofermentation process, what enzymes has interesting property that it can evolve hydrogen simultaneously with nitrogen reduction? So there are some types of enzymes which takes up nitrogen from the environment in during the light, in the presence of sunlight. It takes up the nitrogen from the environment and involve hydrogen. So these are some special enzymes which are known as nitrogenase because they take up the nitrogens. So nitrogenase are those enzymes. So photofermentation is a process in which certain types of bacteria called phototropic bacteria use light to produce hydrogen gas or other organic compounds from organic matter or waste products. The process involves growing the bacteria in a bioreactor under controlled conditions with the source of light and a supply of organic materials such as sugar or waste products. The bacteria use light energy to convert organic material into hydrogen gas and other byproducts, which can be then collected and used as a fuel or chemical feedstock. So, in this way, we can use these phototropic bacteria. We can utilize this phototropic bacteria to convert it into hydrogen, which is a type of fuel for us. So, and this process is known as photofermentation. That this fermentation of biomass or organic matter. So, the fermentation of biomass in the presence of photons or light is known as photofermentation, and this is done by some bacteria which are known as phototropic bacteria. And these phototropic bacteria take up the nitrogen from the environment. Therefore, these are also known as nitrogenase. Therefore, the correct answer for this was nitrogenase bacteria. So, photofermentation has a potential to be a sustainable and renewable source of hydrogen and other chemicals and is being researched as a possible alternative to fossil fuels. You might have been listening a lot that hydrogen power, we are working a lot on hydrogen power. So, this is also, there are many methods to convert to produce hydrogen, but this is also a clean method to produce hydrogen. So, nitrogen is an enzyme complex found in certain bacteria that catalyzes the conversion of nitrogen to ammonia, a form of nitrogen that can be used up by the plant microorganisms. So, this bacteria takes up the biomass and solar energy. In the presence of solar energy, it converts the nitrogen, atmospheric nitrogen, to ammonia, and also produce biohydrogen. So, therefore, this bacteria has a advantage to produce biohydrogen, which can also work as an alternative green fuel. Now let's move on to the next question. Which biogas cleaning technology is used for removing hydrogen sulfide mainly? So there are many different types of processes in which we can remove the hydrogen sulfide from our from a mixture of gases, and biofiltration is the most used in case of biogas cleaning. Scrubbing is so biofiltration is the most used, and after that is the scrubbing method. So we will discuss these two in the next slides. Biofiltration works with the use of microorganisms that can oxidize hydrogen sulfide to sulfuric acids. So what these microorganisms do is these microorganisms convert the hydrogen sulfide to sulfuric acids, which are then converted to which are then reacted with an alkali or base in order to neutralize them. And after this neutralization, we can get what is we can get a safer uh, chemicals. Biofiltration can be effective at removing some concentration from biogas. It is not typically the primary method for removing hydrogen sulfide. It is not the primary method, but from biogases, biofiltration are used. And this is because hydrogen sulfide is highly toxic toxic and corrosive gas that can damage the biofilter media and reduce the efficiency of biofiltration process. Additionally, hydrogen sulfide can inhibit or even kill the microorganisms that are responsible for breaking down the contaminants in the biofilter. Therefore, some other process such as scrubbing is also used. So, biofiltration and scrubbing both can be used to remove the H2S. In case of biofiltration, the biogas will be fed to a reactor which will contain a filter bed containing some microorganisms. These will be containing some microorganisms and these will react with the H2S and convert it into H2SO4. During this, we can also treat it with alkali so that we can get a neutralized form as a byproduct. So therefore, we can get H2S3 biogas. And there is a second method also apart from biofiltration, that is scrubbing. So scrubbing is a biogas cleaning technology that is mainly used for removing H2S due to its high efficiency, simplicity, and low cost. It is the most used and cost-effective method. In the scrubbing process, the biogas is passed through a liquid, typically alkaline solution such as NaOH, calcium hydroxide, or potassium hydroxide, which reacts with H2S. So the H2S reacts with the alkali such as NaOH, and then it is converted to sodium sulfite and water. So therefore, this and it is a less harmful product and it is a highly efficient and simple method plus a low cost method. So therefore, scrubbing is also used to remove the hydrogen sulfide from the biogases. What is the percentage of waste that can be generated from the mango processing industry? So, in the mango processing industry, we know that in mangoes, mostly there are wastes such as the outer covering, and the largest thing that is the waste is its seed. So, therefore, 25 to 40% can be the percentage of waste which are produced from the mango processing industry. Therefore, mango waste is a very good potential for the biomass waste. So, mango processing industry generate a significant amount of waste in the form of peels, seeds, pulp, and other byproducts. The percentage of waste generated depends on various factors such as efficiency of the processing, the variety of mango juice, and the final product. Generally, the waste is around 25 to 40%, but this may also go up to 40 to 50% depending upon the seeds and the pulp in it. Now, let's move on to the next question. Methanol fueled vehicles use M85, a mixture of 85% methanol and 15% off. So we know that most of the, if we have to guess the answer, then the answer is simply gasoline, because gasoline are mostly used for uh, vehicles. So coming to the question, M85 is a commercial name for methanol based fuel, but pure methanol cannot be used. So only 85%, hence it M85 is name is used, and the rest is gasoline. Therefore, the answer is gasoline. So M85 is a fuel blend that contains 85% methanol and 15% gasoline or petrol, which we know by this name. It is a it is used as a fuel for vehicles that have been modified or designed to run on methanol fuel. Methanol is a type of alcohol that is produced from natural gas, coal, biomass, and is a renewable and sustainable alternative to gasoline. M85 is also used in some countries such as an alternative to gasoline in flexible fuel vehicles, which are designed to run on a variety of fuel blends with different ethanol and methanol concentrations. So let's move on to the next question. In 1956, Jasubhai J. Patel developed a design of what type of digester, which is now popularly known as Gobar gas plant. So in 1956, Jasubhai J. Patel developed a floating drum digester plant, which is popularly known as Gobar gas plant. So he was the first from India to design the first floating drum biogas. Floating drum plants consist of an underground digester, cylinder shape. It is a type of cylinder or dome shape and a moving gas holder. This gas holder floats either directly on the fermentation slurry or in a water jacket of its own. The gas is controlled in the gas drum, which rises or moves down. So this goes up and down, and this gas drum is prevented from tilting by a guiding frame. When biomass is produced, the drum moves up, and when it is consumed, so if the drum floats in a water jacket, it cannot get stuck, even in substances with high solid content. After the introduction of cheap fixed, so this was the mostly used form of digester. This floating drum digester was then in 1960s, I think in 1962 it got commercialized and it was accepted in many other countries. But later on, the uh, the Chinese introduced a cheap fixed dome model, uh, which then replaced these floating drum model. Floating drum pellets became obsolete as they have high investment and maintenance cost along with other design weakness. The drum goes down. So in 1962, Patel's design was approved with the Khadi and the Village Industrial Commission of India, and this design soon became popular in India and the rest of the world. This uh, design is divided into two parts. The tank has a cylindrical dome made of stainless steel that floats on a slurry and collects the gas generated. Hence, the name is given floating type gas holder. And this slurry is made to ferment for about 50 days. More gas is made by bacterial fermentation, leading to pressure inside the gas. The gas can be taken out through an outlet pipe. The decomposed matter expands and overflows into the next small holding tank. This was the most uh, favorable design to produce the gas, but later the arrival of fixed dome replaced these floating dome. So let's move on to the last question. Which is the low pressure method for production of methanol? So there are various methods of production of methanol, and out of these, the ICI or the method made by empirical chemical industry was the lowest, was the method which uses a low pressure of nearly 50 bars. So the ICI process for methanol production was a catalytic conversion of syngas into methanol. So they used the syngas to produce methanol. So, but before this, we need to produce syngas. So this involves four steps, and among these four steps, the first was production of syngas. The syngas is typically produced from natural gas, coal, or biomass through a process known as gasification. So the gasification process involves the partial oxidation of feedstock at high temperature to produce mixture of hydrogen and carbon monoxide. So we have seen this in previous weeks also, that we can do the gasification of the coals or biomass, which can be we can do at high temperature to produce hydrogen and CO, which is known as syngas. After this, we need to purify it so that in order to remove the impure things, So this gas is then purified to remove impurities such as sulfur, carbon dioxide, and water, and we get is what is known as pure hydrogen and pure carbon monoxide. This pure combination of hydrogen and carbon monoxide is known as syngas. After this, we convert this syngas into methanol. The third step is to convert this syngas to methanol. So the purified syngas is then fed into a reactor containing a copper-based catalyst. So it is sent to a reactor which has a copper in it. So it has a copper-based catalyst that promotes the reaction between hydrogen and monoxide. So these two gases are reacted with itself in the presence of copper inside a reactor to produce methanol. So this was the cheapest method to produce methanols. And how were we creating these syngases? We were doing this by gasification process, which were done at high temperature. So in this way, we are converting the biomass to syngas and then converting the syngas to methanol. This was the cheapest method, and it required a very low pressure of nearly 50 bar. So the crude methanol is finally the distillation. So the crude methanol is then separated from these unreacted syngas and other byproducts, and then this crude methanol is purified through a distillation process to remove any impurities. The ICI process for methanol production is widely used in the chemical industry and has been refined over the years to improve efficiency and reduce cost. Now let's move on to the next question. Methanogen bacteria can exist in a pH range between approximately 6.8 to 8.2. Any overproduction of acids below or above this pH limit will limits the bacterial age, kill or inhibit the growth. True or false? So yes, methanogenic bacteria has a very tight range of pH in which they exist, and uh, is in this process, if there is any overproduction of acids and the pH goes below 6.8 and it becomes acidic, so the it will lead to the killing of these bacteria. Therefore the answer is yes, true. Any deviation from this range, especially towards acidic condition, can inhibit or even kill the methogenic bacteria. In biomass conversion, methogenic bacteria are commonly used in aerobic digestion process to convert organic matter into biogas, which is a mixture of methane and carbon dioxide. So the bacteria breaks down complex organic molecules into simpler compounds such as fatty acids, alcohols, and sugars through a series of biochemical reactions, ultimately producing ethanol and byproducts. So methylgenic bacteria are used to produce methane gas majorly. Therefore, its name is methylgenic bacteria. And if there is a uh, high amount of acid production during this, if the acid production goes high, the pH will go lower, which will result in killing of the bacteria, which has an octane number of 113 and a density that is about half that of gasoline. So the answer for this is methanol. Methanol has a octane number of around 108 to 115. So the answer is methanol. Gasoline has the lowest octane number of 91 to 94, while methanol has the highest among this, that is in the range of 108 to 118. So therefore, the answer is methanol. So thank you everyone for uh, this week coming to this week, and I hope this session will help you to solve the questions of the assignment 8, and we'll meet you next week, in which we'll discuss the some we will discuss about some preparatory questions for your week 11. So thank you, and we will meet you next week.